So you can see my screen, right?
Yeah. Yeah. Can you make it a little larger?
Yeah. Yeah.
Oh, you have typed it out. Okay, that's very nice.
Yeah. So basically, we will talk about a Hardy-Littlewood maximal function and its relation to something what we call as averaging problem. And there is a concept of differentiation of measure that you already did, uh, and how to interpret that in a different way. So that's the basically main thing of this presentation. Okay, so let's see. Yeah, I'll just make this a bit larger. So let's think of this example. So suppose you have a function from the closed interval ab to the real number and is integrable. It's given that the function is integrable. So then what happens is that you want to define this function fx, which is just integral of my main function from a to x. And then you want to differentiate this function. So basically your f prime x is equal to limit h tends to 0, 0, f of x plus h minus fx by h, which is nothing but limit h tends to 0, 1 over h, x to x plus h, fy dy. So if you want to calculate the derivative, you basically want to calculate this limit actually. So this can also be thought of in a different way, that if you think of x to x plus h as an interval, then this is nothing but 1 over the measure of the interval, and then you integrate over the interval of this function. So that is another way to think about this. And so you want to calculate the limit as measure of this interval go to 0. So it can be treated as a kind of average value of f on the interval f. So that's the main point. So that's why it's also known as some sort of averaging problem. So we will see. Right. So what you expect is that this average value will tend to the value of f at the point x, isn't it? I mean, at least you know that if your function f is continuous, then this value will obviously tend towards the value of f at x. Because whenever you go, I mean, close to x, this fy will be approximately equal to f of x, and the length of this interval is h. So ultimately this limit will turn out to be f of x. So for continuous function, this is clear that this average value will be equal to f of x. So for continuous function, this is obvious that the derivative of my integral function will be equal to the value of the main function. So on the other hand, let's take another scenario, which is that suppose my mu is a measure which is absolutely continuous with respect to the standard Lebesgue measure. So nu is your measure which is absolutely continuous with respect to the standard Lebesgue measure on the Borel sigma algebra. So you know that there is a radon-Nicotian derivative of mu with respect to m. I mean, obviously, if mu is some well-behaved measure, that is, I mean, it's sigma finite and all. But apart from that, I mean, you know that, I mean, there should be a radon-Nicotian derivative. Okay. So exactly like previously, you calculated the derivative of capital F in this manner. Suppose you also want to calculate the derivative of the radon-Nicotian derivative in this way. You want to take the limit r tends to 0, the nu of some ball by the Lebesgue measure of some ball. So let's say, yeah, so this is my ball. And then you want to compare the measure nu and divide by the Lebesgue measure of this ball, and then take the limit as r tends to 0. So that's how you want to calculate the radon-Nicotian derivative of nu with respect to m. And you know that this nu is given by an integral with respect to the Lebesgue measure. So that means measure of this ball, the nu measure, will become integral of some function over the ball. So basically you want to calculate this limit. This is the limit you want to calculate. This is just the 1/, measure of the ball, integral of the function f. So f is basically your radon-Nicotian derivative. And then you want to take the limit as r goes to 0. And then the best you can expect is that this will be exactly equal to f of x. This limit will be equal to f of x for almost everywhere, for almost every x. So, I mean, that is the main target. That is the main goal of this presentation. I mean, how to do this. So again, for continuous function, this is obvious as before. I mean, for continuous function, there is no question about it. Obviously, this limit will be equal to f of x. I mean, that is for every x. That is more better actually. So we want to show that this for certain class of functions, this limit will exactly be equal to f of x for almost every x. Okay. So this is known as averaging problem, because basically you are looking at a ball centered at x of radius r, and then you are calculating the average value of f around that ball. And you want to take the limit as r goes to 0 of that average. So this value will be equal to fx or not? That is the question. So here's the definition, which is that we denote the space of all locally integrable functions and Rns by L1 Rn, L1 local Rn. So by locally integrable function, I mean that integral of f on a bounded measurable set that is finite. So that is what I mean by locally integral functions. So basically you can think of like for every point there is a bounded measurable neighborhood such that in that neighborhood integral of f is finite. So that is the definition of locally integrable functions. Now the theorem we will prove is that if my f is a locally integrable function, and then I take this average value of f over the ball of radius r centered at x, and then I take the limit as r goes to 0, then value will be equal to f of x for almost every x. So that is the theorem we wanted to establish here. So I will just denote this average value by AR of fx. So AR just stands for average value of f on the ball of radius r centered at x. So this is my average value. And then I want to show that this average value will go to this expected limit. Yeah. So is the problem clear for everyone? I mean, what do you want to show?
Oh, your
Yeah.
presentation is on.
Yeah. I'm just switch the presentation. I'm just
Oh,
yeah. So it's okay for everyone, right? I mean, just so in some sense, this will be a generalization of fundamental theorem of calculus. Because in fundamental theorem of calculus, what we had is that we know that for a continuous function or for a continuous almost everywhere function, the derivative of the integral is equal to the, I mean, value of the function actually at that point. And now you are replacing this continuous function by a local integrable function, and then you are going to this measure setup. So that's the main thing. So that's how it's generalizing the notion of differentiation in Euclidean space. Yeah. For example, just think of this. I mean, here you had age actually. When you're calculating the limit, here you have some age. You're replacing that age by the measure of the ball, and then again integral of f over this interval by integral of f over the ball. So that's how this differentiation in Euclidean spaces is generalized to the concept of differentiation of measures. Right. So yeah. Okay. So first we will start with the technical lemma. This is a very well-known lemma in combinatorial geometry. So this is known as Vitali covering lemma. This lemma itself is very interesting and important. So what Vitali covering lemma says is that, okay, so I will just draw something. Yeah. So Vitali covering lemma, what does it say is that suppose you have a finite collection of balls. So you have some finite collection of balls, say B1, B2, B3 to Bn. Then you can find a finite disjoint subcollection, suppose Bi1, Bi2 up to Bik, such that the union of all these balls, union of Bj, j is equal to 1 up to n, this is completely covered by 3 times each of these balls in the subcollection. Yeah.
What do you mean by 3 times the balls?
Yeah, sorry, I can't hear you.
No. What do you mean by 3 times balls? Is it the measure or what?
Yeah. So 3 times balls means it's the concentric ball with 3 times larger the radius.
Okay.
Yeah. Right. Yeah, right. I should say that. So suppose this is my ball B, center is X. So by 3 times of B, I mean the ball with the center X and the radius 3 times larger than the original ball. So this is like this. Yeah. So what Vitali covering lemma is saying is that you have a finite collection of balls, and then you can find a sub collection. Moreover, it's a disjoint collection such that the whole collection is covered by, I mean, 3 times my sub collection. So we will see, I mean, how this is useful in proving something, proving the result actually we want to show. So these are technical lemma. Okay, the proof is not very hard. So for the proof, what you do? So suppose you have these balls, let's say. Suppose you have these balls. So what you do is that you choose the ball of the largest radius. You start with a ball of the largest radius, and let's call it bi1. Then look at all the balls which have a non-empty intersection with bi1. Then all of those balls which have non-empty intersection with bi1 will be covered by 3 bi1. So do you agree with that? So because you were starting with a ball of the largest radius, so just remember that.
In fact, if you take just 2 balls, then this logic of 3 becomes very clear.
Yeah, exactly.
Yeah, you just take 2.
Yeah, right. So suppose this is the ball of largest radius, so you can just look this pairwise and take another ball. And remember that this ball's radius is obviously, I mean, not larger than this radius, because I have chosen this radius to be the maximal radius. Then obviously these 2 balls can be covered within 3 times the ball of the maximal radius. So you can
Yes,
just directly, you can just, yeah, so you can just directly show it. So you can take any point here. Suppose this is y, and suppose this point is x, and take another point z in the intersection. Then just apply triangle inequality, because your d of xy is less than or equal to d of xz plus d of zy. Your d of xz is less than or equal to r, and d of zy is less than or equal to diameter of the smaller ball, which is just 2r. Yeah, so it's 3r. So just basic normal triangle inequality. So I mean, similarly, I mean, all the balls which have a non-empty intersection with the ball I have chosen with the largest radius can be covered by 3 times the ball I have started with. So now just go by the induction. So I will just go back to the slide. Yeah. So that is what I've written here. I mean, choose the ball with the maximal radius and then look at the balls which intersect bj1. Then all of these balls can be covered by, I mean, 3 bj1. Then what do you do? Then look at the remaining balls which do not intersect bj1. Look at the remaining balls which do not intersect bj1, and among those balls, you choose the ball of largest radius and call it bj2, and repeat as before. And observe that this subcollection will be disjoint by your choice, because I am choosing bj2 to be the ball of the largest radius among the balls which do not intersect bj1. So by my choice, this collection is it's disjoint. So that's how you get the subcollection. So the proof is not very hard, just some basic observation. So now using Vitali covering lemma, we can just prove another corollary. And exactly this form of the corollary will be useful for us. Yeah. So I'll just draw another picture. So this is saying that take an arbitrary collection of open balls in Rn. So I'm taking an arbitrary collection of open balls in Rn and looking at their union. So this is my open set. Union of Bi. I belongs to some arbitrary indexing set, and this Bi's are open balls. Then you know that this open set has a Lebesgue measure. Let's call it mu, and take some real number C, which is less than measure of U. Then you can find a finite disjoint collection of open balls B1, B2 up to say Bn, such that measure of this finite collection is greater than or equal to C by 3 to the power n. And note that this n is fixed. I mean, if you are in a fixed dimension Rn, your n is also fixed. So what this is saying is that, I mean, whatever collection you have, look at the measure, look at the Lebesgue measure of this collection, and take something C, take a real number C, which is very close to this, and then you can always cover a fraction of C. So it's almost the fraction of the total region U, which can be covered by just finitely many balls. So again, the proof is not very hard. Yeah, so there is a statement. C is a collection of open balls in Rn. Take the union. Then there is a disjoint collection of open balls, such that measure of balls, sum of the measure of these balls is greater than C by 3 to the power n. So what you do is that you use the inner regularity of the Lebesgue measure. So if C is less than the measure of U, then you can find a compact set K such that measure of this K is greater than C and less than measure of U. K is contained in U. This is just the inner regularity of the Lebesgue measure. And then you know that your K is, since U is covered by these open balls, your K is also covered by these open balls, and then use the compactness. Then you get a finite subcollection. So K is covered by some finite number of balls. Yeah, K is covered by some finite number of balls, and then again use the Vitali covering lemma. From that finite subcollection, you get a disjoint subcollection of open balls B1, B2, Bk, such that that collection is covered by 3 times that subcollection. So your compact set can be covered by 3 times this disjoint subcollection. So your C is less than the measure of K, and this measure of K is less than sum of the measures of the balls 3bi. And in dimension n, I mean, remember that the measure of Ca is just C to the power n times ma. So in dimension A, if you scale a set by a constant C, your measure will scale by a factor of 3 to the power n. So that's how you get this. So you can always cover a fraction of your whole region U by a finite number of disjoint balls. Whenever C is something less than mu, your sum of the measures of these balls is greater than C by 3 to the power. So that is the corollary. Yeah. Yeah. So I think the proof is, not very hard. So we will exactly use this corollary to prove that my average value of f will tend towards the value of the function at that point if the radius of the ball goes to 0. So yeah, this thing. For almost every x, we want to show this. If f is locally integrable function, because if you don't have a locally integrable function, then this average value is not defined, right? For this average to be well defined, you need f to be integral locally on open balls. So that's why you have this assumption that my f has to be locally integrable, and then we can say this. Yeah, so let's go to the proof. Right. So for doing the proof, first we will define a very important operator, which is known as Hardy-Littlewood maximal operator. So given any function which is locally integrable on Rn, this is how you define your Hardy-Littlewood maximal function. So what you do is that you take a center x, you look at the ball of radius r, and then you look at the average value of the function mod f. Instead of f, we are looking at mod f precisely. So look at the average value of mod f on this ball, and then take the supremum over all positive r. So that is what it's written here. So your f is given. So at a given point x, your hf of x is defined as supremum of the average value of mod f over all positive r. So that is the main thing. So you look at the average value of mod f around a ball, and then you want to see, how far can you enlarge this average value by varying the value of the radius. So that is your Hardy-Littlewood maximal operator. And then we try to prove a weak type inequality. This is known as some sort of weak estimate for this Hardy-Littlewood maximal function, which is known as maximal theorem. One thing easily you can see is that my Hardy-Littlewood maximal function is a measurable function. So can you see that? This is very easy to see. So firstly, just observe that this AR mod fx, this intuitively clear that this is a continuous function in R and X. If you look at this function AR mod f at a point X, this is intuitively clear that this is continuous jointly in two variables X and R. Maybe you want to prove this, but I think this is intuitively clear that this function is continuous. And then you are taking supremum over all positive R. So your HF will also HF will be a measurable function. So then you can talk about the measure of this set. You fix a positive alpha, then look at the set of all x where your maximal function, the value of the maximal function exceeds alpha. You can look at this set and then look at the measure of this set, Lebesgue measure, and that is bounded by some constant times the L1 norm of f. So this inequality is, I mean, seems very similar to the inequality of Chebyshev inequality or Markov inequality, whatever you call it. And all of this kind of estimates are known as weak type estimates. So measure of this set is bounded by some uniform constant times the L1 norm of f. Okay, so let's prove this. So you define a set E alpha to be the set of all x such that each of f x is greater than alpha. So you want to show that your measure of E alpha is bounded by that thing. So for each x in E alpha, you get a positive radius. Let's call it Rx, such that average value of mod f on the ball of radius Rx is greater than alpha, right? This just follows from the definition. Because my Hardy-Littlewood maximal function is the supremum of all those AR mod f x. So if the supremum is greater than alpha, then at least there is one R such that this AR mod f x is greater than alpha. So for each x, I get an open ball around x, such that average value of mod f on that open ball is greater than alpha. And then for every point of x, you do that. So you get a covering of E alpha. Bxrx, that gives you a covering for E alpha. And then take a constant C, which is less than the measure of your set, measure of E alpha. Then by Vitali's covering lemma and the corollary we proved, there are finitely many disjoint balls Bj such that your C by 3 to the power n is less than sum of the measure of these balls. So just recall the corollary. So yeah, this was what corollary did. Sum of the measure of the balls is greater than C by 3 to the power n. So that's how you get this. Your C is less than 3 to the power n times sum of the measure of the balls. And then measure of each of the ball is less than or equal to integral of mod f over that ball by alpha. And then this is less than or equal to the integral of mod f over whole Rn. So this integral is just over this disjoint open balls. I'm just extending the integration to the whole of Rn. So obviously we will have a less than or equal to sign. And this is nothing but the L1 norm of alpha. So that is a proof of the maximal theorem. So this is your weak type estimate for your maximal operator.
Hello, Soumyadev.
Yeah.
So, are you assuming that this measure of E alpha is greater than 0? Or this C can be negative also?
Yeah, let's say C is positive.
So, you are assuming that this measure of E alpha is greater than 0.
Yeah, this is my Lebesgue measure.
Okay.
Yeah. I mean standard Lebesgue measure, so it's not a sign measure or something.
No, I'm saying this particular set have non-zero measure. This EL.
Yeah, right. So
If it has zero measure, then there is nothing to prove.
there's nothing to prove.
Yeah.
If it has positive measure, you assume a positive C which is less than that and just go like that. So you have a weak type estimate of this. So measure of this set cannot be too large. It's bounded by something. It's bounded by the L1 norm of F up to a constant. Okay. So then we will use this maximal theorem to prove our averaging problem. Okay, yeah, so I think the proof is clear. So I'm taking a positive number C, which is less than the measure of this set. And then I've shown that for every such C, my C will be less than or equal to this thing, 3 to the power n by alpha norm of F. Then you can just take C tends to measure of E alpha. For every, because for every C less than M of E alpha, this is true. So you can just take C tends to measure of E alpha. So from that it will follow that your measure of alpha itself is less than or equal to this thing, 3 to the power n by alpha norm of F, L1 norm. So this is the thing, yeah. Right. So letting C tends to M of E alpha, we obtain the desired result. So now we are finally ready to prove the averaging problem or averaging theorem for local integrable functions. So you take any locally integrable functions on Rn. Look at the average value of f on the ball of radius r. Take r tends to 0, and that will be equal to f of x for almost every x. So it suffices to show that for every natural number n, I mean this holds for all mod x less than or equal to n. For every fixed natural number, if you show that with mod x less than or equal to n, this is true, then obviously this is true for all x, almost every x in Rn. And you are taking r tends to 0. So you are only interested in the value of ARFX when r less than or equal to 1. You can just do that because you are letting r tends to 0. So your value of ARF will only depend on the values of Fy for mod y less than or equal to 1, n plus 1. So you're restricting your region to, I mean, mod x less than or equal to n region and taking r less than or equal to 1. So your value of ARFX will only depend on the values of the function f in the region mod y less than or equal to n plus 1, right? Yeah, because this is my radius n, and then you are taking r to be at most 1. This is just for some simplification. We are doing this. I mean, so it's given that your f is locally integrable. So by replacing f by f times the indicator of the ball of radius n plus 1, you can assume that f belongs to L1R. So we just use this to simplify the problem. Without loss of generality, you can assume that f is L1 instead of locally L1. So if it's locally integrable function on Rn, then replacing f by f times indicator of the ball of radius n plus 1 centered at 0, you can assume that f is in L1. So the point is that we want to use some nice properties of the space L1R. Okay. So what is the idea of the proof? Idea of the proof is that first you try to approximate f by a continuous function, because you know that for continuous function this always holds. For continuous function there is no issue. So you try to approximate f by a continuous function and then estimate the rest using Hardy-Littlewood maximal inequality. So that is the idea of the proof. So how do you approximate it? How do you approximate a function in L1 by a continuous function? And that is very easy. So you know that there is a dense subspace of continuous functions, right? For example, your CCR, the compactly supported continuous functions, is dense in L1R, right? In the L1 norm, you know that. Your continuous, compactly supported continuous functions is a dense subspace of the space of all L1 functions. So basically, you can approximate your function f by continuous functions in the L1 norm. So given any positive epsilon, we can find a continuous integrable function g such that integral of mod of g minus f is less than epsilon. Okay. And then use the continuity of g. You know that this g is continuous. So if you take r tends to 0, then argx will tend to gx because g is continuous. For g, you don't have any problem. Because if your y is sufficiently close to x, then g will also be sufficiently close to gx. So for every epsilon, I can choose a, okay, let's say for every positive delta, I can choose a small r, such that whenever mod of y minus x is less than r, my mod of gx minus gx is less than delta. So then this thing will be less than delta times measure of the ball, and then I have 1 over measure of the ball in front. So that will cancel out, and that will give me less than delta. So for every positive delta, you can do that using the continuity of g. So as r tends to 0, your average value of g will tend to the value of the g at the point. So this is your x and this is your ball. You look at the average value of g on this ball and then take r tends to 0. That will tend towards the value of g at the point x because g is continuous. But we want to show it for f, for almost every x. So for that, we try to estimate this quantity, lim sub of mod of arf minus f as r goes to 0. Then use the triangle inequality. So you write this as ar of f minus g, then arg minus g, then g minus f. So you split this into 3 parts, and then the first part is the first part is dominated by your Hardy-Littlewood maximal function by definition, because Hardy-Littlewood maximal function was defined as the supremum of all the average values when the supremum is taken over all r positive. So obviously this will be dominated by your Hardy-Littlewood maximal function. This thing will go to 0 because of the continuity of G, and the rest is just mod of A minus. So now you only have to estimate these two things, your Hardy-Littlewood maximal function of F minus G and mod of F minus G. And this is your limit. So this is then you apply the standard trick. For every positive alpha, you define a set. For every positive alpha, you define a set like this. Set of all x such that mod of ARF minus F is greater than alpha. And define F alpha to be set of all x such that your mod of F minus G is greater than alpha. Then obviously we have E alpha is contained in F alpha by 2 union the set of all x such that Hardy-Littlewood maximal function at F minus G is greater than alpha by 2. This is clear, right? Because if this lim sup is greater than alpha, then at least one of these has to be greater than alpha by 2, right? So that is what we are saying. See, if this is greater than alpha, then at least one of these has to be greater than alpha by 2. So that is another way of saying that E alpha has to be contained within F alpha by 2 union the set of all x such that each of F minus G at x is greater than alpha. So your measure of E alpha will be less than or equal to sum of the measure of this two set, and then you show that, then you try to show that measure of each of this set is very small. So that is very easy. So your on F alpha, the difference of F and G is greater than alpha. So you can see that integral of mod of F minus G over the set F alpha by 2 will be greater than alpha by 2 times measure of F alpha, right? And you know that this quantity is less than epsilon. This is from the approximation. We approximated F by a continuous function G, so that the L1 norm of F minus G was less than epsilon. So from that it follows that this thing is also less than epsilon. So your alpha by 2 times measure of F alpha by 2, that is bounded by epsilon. So you have estimated the first part. Yeah, you have estimated this measure of this set. So your measure of this set will be bounded by 2 epsilon by alpha. Yeah, and then how will you estimate the measure of this set? This is just maximal theorem. We proved that measure of this set will be bounded by 2 into 3 to the power n by alpha into L1 norm of F minus G. This is just the Hardy-Littlewood maximal estimate. So this is bounded by 2 into 3 to the power n by alpha times the L1 norm of F minus G, and measure of F alpha by 2 is bounded by 2 epsilon by alpha, and then you are done. Then your epsilon is arbitrary positive real number, so you can take epsilon as small as possible. So that will give measure of E alpha to be 0. So what we have done is that for a fixed alpha, I was looking at the set of all x such that mod of AR minus F is greater than alpha, and we have shown that the measure of that set equal to 0. Yeah, so that is what I have written. And then you take any x which is outside this E1 over n. You take any x which is outside, say, E1 over, union of E1 over n. Each of E1 over n has measure 0 because we have proved that for any positive alpha, measure of E alpha is 0. So measure of E1 over n is 0. So measure of the union of E1 over n greater than or equal to 1. Measure of this set is also 0. And you take any x which is outside this set. Then obviously my lim sup will be 0, right? Because I defined E alpha to be the set of all x such that the difference exceeds alpha. And we have shown that the measure of that set is equal to 0. So if you take any x which is outside this set, then this lim sup will be 0. The lim sup of mod ARF minus f as r goes to 0 will be 0. And that means limit r tends to 0, your ARF will be exactly equal to f of x. So that is what we wanted to show. So yeah, so for locally integrable functions, if you look at the average value of f around a ball of radius r, and then you take limit as r goes to 0, that will be exactly equal to the value of f at the center for almost every x. So you can actually calculate your radar Nicodemus derivative by calculating this limit. If your nu is absolutely continuous with respect to the Lebesgue measure, then you know that your nu is given by integral of f against your Lebesgue measure, and then you divide by the Lebesgue measure of the ball. So you are basically comparing nu and m, nu and your Lebesgue measure on the open ball, and your limiting ratio is the radon derivative. So you can actually calculate your radon Nicodemus derivative in this way. And obviously, as I said earlier, this is really a generalization of fundamental theorem of calculus. So in fundamental theorem of calculus, what happened? You had this 1 over h and then integral over x to x plus h. And now what we have showed is that if f is any locally integrable function, f need not be continuous. F is any locally integrable function, and they interpret this h as your length of the interval x to x plus h, then this is just the theorem we proved. So really this fundamental theorem of calculus, which is just differentiation, normal differentiation in Euclidean space, is really a special case of differentiation of measure. Yeah. So yeah. So I think that is all I wanted to say.
Thank you.
So,
Thank you. Thank you. Nice presentation.
yeah. So any questions or comments or anything you want to add?
Yeah, I have nothing to say. So others, yeah.
Yeah.
Yeah, hello.
Yeah.
Yeah, sure, sure.
Yeah. So, I mean, this is for people, I mean, who sort of like cricket, maybe. This is a very historical anecdote. Sort of, Hardy, when he did this, he made a little joke that he interpreted this maximal function
Cricket.
as
You are talking about
the
cricket.
supreme of the averages. Yeah,
I mean, run of the batsman, right?
yeah. You heard about it, right? Yes.
Oh, I didn't know that. What
Yeah,
is
Yeah,
the
it?
yeah,
bat,
actually.
the batsman
So
when the batsman wants to increase his average,
Mhm.
but and the bound is and the alpha is in the denominator. So it sort of says that the batsman's the batsman's satisfaction is the most when his average is the best, right?
Yeah, yeah.
The batsman's, so it sort of says that the batsman only remains satisfied when his runs are declining, something
Okay.
like that. Yeah,
Okay.
yeah.
Okay.
so basically
Okay. So
you want to maximize your average value by varying R.
Yes. So
And
you
yeah, right.
can
And that
only
has
maximize it when that alpha decreases, right? I mean, as your alpha
uh,
decreases. Actually, you have to
yeah,
make,
yeah,
I mean, convert it into a discrete version, but maybe you can see it in continuous.
yeah, yeah. I mean, yeah. So also there is a modified version of Hardy-Littlewood maximal function. So I mean, instead of just looking at the ball of radius r, you can take any ball which contains the point x. You can take any
Okay.
ball. So that is your modified Hardy-Littlewood function. So that is just you take the supremum over any ball which contains a point x. So not necessarily x has to be the center of the ball. You take any ball which contains x and supremum, take the supremum of this quantity 1 over measure of b on the ball integrate mod f. Right. So let's call it a star. This is your modified Hardy-Littlewood function, and I think then you can show that this a the if you want to analyze a star f or you want to analyze your original HF, this these two things are not very different. I mean, they're almost their behavior is almost same because these are some sort of bound like this. I mean, A star f is bounded by h of f and 2 to the power n h of. So originally, I think Hardy-Littlewood started with this function. Actually, you can take any ball.
Constant integrable. Okay.
Yeah, yeah, 2 to the power n times h and hf. A star f is bounded by this. This is a slight modification of our Hardy-Littlewood maximal operator. Just the behavior is same. I mean, it doesn't matter. So yeah, I mean, so that is the idea. I mean, basically, whenever you want to prove something in the L1 space, you have a very nice dense subspace. You approximate by that always, and you approximate the rest by some inequality that you have. So that's the main idea. Yeah. So yeah. So thanks for
okay, now
listening.
now it is. Hmm. Oh, it's Oviroop's presentation now.
Yes, sir.